This is lecture 5 for week 5 of CS 1030. And in this lecture segment, we're going to look at a different way to convert from a number to base 2 or binary. And so if you remember, what we looked at a left to right algorithm for finding a binary number, for finding the binary representation of a number in the last lecture segment. This time we're going to look at an algorithm that works in the other direction. So let's take a look at the algorithm. And so this one I think is maybe a little easier, maybe a little simpler to understand than the other one. In any case, so we input a number y, and now while y is greater than 0, we divide y by 2, and there may or may not be a remainder. And of course, when we divide a number by 2, the remainder has to be either 0 or 1. So now we add the remainder r to the new binary number, to the sequence of binary digits that we've stored, and we do that going from right to left. Okay, so that's all there is. That's all there is to this algorithm. It's really, really, really easy. So let's see how it plays out. So if you remember in the last segment we worked with the number 13, so let's do that again. So y is 13. And so how do we do the algorithm? Well, while y is greater than 0, so it's greater than 0, so we execute the loop body, we set y to y divided by 2, and we remember the remainder. So 13 divided by 2 is 6, remainder 1. So the binary number that we have so far, and remember we're going to work from right to left this time, is just 1. And so when we, in the next loop iteration, we're going to add a number, a binary digit to the left of it, and so on until we're finished. Okay, so at this point, y is 6, and we execute the loop body again. So in the second iteration of the loop, we set y to 6 divided by 2 equals 3, and this time, since it was an even number, we get a 0 remainder. So the new y is 3, and our binary number, we tack on to the left side of it a 0, because that was the remainder. All right, so 3 is our new y, so it's still greater than 0, so we execute the loop body again. And now we get 3 divided by 2 is equal to 1, remainder 1. So since the remainder was 1, we append onto the left side of the binary, our ongoing development of the binary number, a 1. And we don't terminate yet because y is still greater than 0. And so in the next loop iteration, we get y equals 1 divided by 2, which is 0, and there's a remainder of 1. So we add that to the left side of the binary number. Now y is 0, so the while loop terminates. It doesn't execute any more iterations. And since that's the last part of the algorithm, since the algorithm was just the while loop, our algorithm terminates. Okay, so the resulting binary number that we got from this algorithm is 1101. And if you remember the binary number we got from converting 13 to binary in the previous lecture segment, it was also 1101, and of course that's good, right? If we didn't get the same answer from two different algorithms to do the same thing, then one of them isn't an algorithm, or one or both of them isn't an algorithm for doing the thing that we hoped it was. So this is really easy. It's a simple algorithm. Again, I think it's even easier than the other one, but it's maybe a little less apparent why it works. And so let's start to understand why this algorithm actually works. Okay. So why did we just look at a correct algorithm for finding the binary representation of a number? So what I want to start with is arguing about the least significant bit. So the least significant bit is the bit at the right side of the binary number. It's in the ones place. And one thing we can observe is that a binary number always has a 1 in its least significant bit if it's odd, and a binary number always has a remainder of 1 when divided by 2 if it's odd. So what we can see is that these conditions are essentially the same. If we had an odd number, if we have an odd binary number, we want to put a 1 in the least significant bit of the binary representation of it. And we can see that the algorithm we have is always going to put a 1 there in the least significant bit if the number was odd in the first place. So at least for the least significant bit, it's clear that this algorithm works. And so something we sometimes do when we're talking mathematically is we use IFF. It stands for if and only if. So if this thing is true and the other thing are true always together or false together, then we can say if and only if. It's just sort of a shorthand that makes it easier to talk about math. Okay, so that was only arguing about the least significant bit. So what I hope I've convinced you of at this point in the lecture is that this algorithm correctly works for the least significant bit. We haven't talked about the other bits yet. So let's look at a different example to start to understand why it works in general. So we're going to look at the number 21 in binary. So if we run that algorithm, then we're going to get this binary representation. We're going to get 10101, and all binary digits to the left of the 4's place are going to contain, or sorry, the 16s place are going to contain zeros. So that's 21 in binary. And now let's talk about how the algorithm was going to process the number 21. So when we divide 21 by 2, what happens is every place that we have a binary 1 digit, it becomes worth half as much. That's what it basically means to divide a number by 2, right? The number becomes worth half as much. So all the components that we add up to make the number also have to be worth half as much. And that works in all bit positions except for the bottom one. The bottom one, we don't have a convenient way to divide it by 2. So that one is sort of a special case. So if we look at 21 in binary, it's 1, 0, 1, 0, 1. 21 divided by 2 is 1, 0, 1, 0 divided by 1. So what we can see is that dividing a binary number by 2 is exactly the same as shifting the digits of that binary number to the right by 1 bit position. And there's a sort of awkward case of what do we do with the remainder, but let's sort of not worry about that for now. So dividing a binary number by 2 is equivalent to shifting it right by 1 place. And then it's going to turn out that multiplying a binary number by 2 by the exact same reasoning, you can accomplish that by shifting it 1 bit position to the left, although we don't need to know that right now. So we shift it to the, so what we've looked at so far is we've looked at an argument that our algorithm works for the least significant bit. And we've also looked at an argument that the division by 2 shifts the binary number over by 1 bit position. And so by putting those facts together, we can sort of see that this algorithm, this hasn't been like a really rigorous proof here, but it's sort of an informal argument that it works. We can see that putting these different observations together, the algorithm, we can sort of uncover the binary digits hidden in the algorithm by running this process for the least significant bit, and then shifting it over, and then using this algorithm to get the new least significant bit. So that's basically why this works. And anyway, so that's all for this lecture segment. Thank you.